So this is finally going to build up to one reason, or to summarize, why did we get done with the last part, right?
Yeah.
Okay, good. Why do you care about polarity? Why do you care about polarity? Well, I think I tried to, well, yeah. Okay, so we said water and oil don't mix because of polarity. And kind of related to polarity is, well, at the crux of polarity is this idea of, will molecule A connect with molecule B? Okay? I said if this is polar and this is non-polar, I guess they won't. Well, they might, but there's a way around that because we're going to try to do that. So how do molecules or atoms or ions stick? How do molecules or ions stick together? How they stick together, I'm going to kind of emphasize intermolecular versus intramolecular. Intermolecular means that you're sticking two kind of units together. Those units could be ions. Those units, one unit could be an ion, one unit could be a molecule, or both units could be a molecule. So the intermolecular bond is talking about kind of connecting those major units together, intermolecular. I want to kind of contrast that to intramolecular forces. Think of the intramolecular forces as the chemical bonds. So hiding that black thing right there, that chemical bond is an intramolecular force. This ... is an intermolecular force. Okay? So that inter. You guys got it. Now it's not done by accident that chlorine would be partially negative, partially positive, partially negative, partially positive. So actually, this is one type of intermolecular bond called a dipole-dipole intermolecular bond. It just means you have two polar things that are kind of connected together by their partial positive and partial negative. Okay, intermolecular bond. As far as stuff being stuck together, if something is in its solid state, you have a high degree of intermolecular bonding. Gases, if they're behaving ideally, they're not stuck to anybody. They're all independent little particles or gas or molecules or atoms. So gases essentially have no intermolecular bonding. Liquids somewhere in between. So intermolecular bonds. This will play. It's been a while since we've seen this one. What we've been talking about, we were in Chem 1. Solids have a high degree of intermolecular bonds. That's why they're rigid. Liquids have a lesser degree. That's why they are fluid. But they have a certain amount that keeps them stuck together so they don't vaporize. Then gases have no intermolecular bonds. And we said actually solids, that's why they keep their volume and their shape. Liquids keep its volume but take on the shape of its container. And gases takes on the shape and the volume of its container. So from left to right, we have increasing kinetic energy. And from right back to left again, we have increasing, IMF stands for intermolecular forces. I think we've covered this before when we talked about phase changes. It takes energy to go from left to right as you have solid, liquid, gas. And as you go from right back to left again, when those bonds are formed, when a gas condenses to a liquid or a liquid freezes to a solid, energy is actually released. And I think we've seen this video before too, but we'll look at it one more time. It's movie day. It's Friday. Print them out for y'all. So this one must be important. They're listed from the strongest to the weakest type of weights to connect repeating units. So if you have an ion connected to an ion, we would call that an ion-to-ion intermolecular bond. Oh, homework. Yay, good job. Was it homework? Oh, you're great. You're fine.
Sorry.
You're fine. You're great too.
Looks like my application turned into this.
Well, good. I hope that comes through for you. Now, I am going to boogie out and move my 4 o'clock appointment to 2 o'clock in Burlington. And so I'm going to boogie out at 1. And I'm going to, these will make more sense when we go through them. This sheet will make more sense when we go through it. Another way that matter can be connected is ion dipole. I will go ahead and write up here, and I'm going to explain it more, is anytime you see these sort of connections, like intermolecular bonds, anytime you see dipole, think polar. So you must have, that guy is polar, and that guy's an ion. Okay, so ion dipole. Dipole, polar. So you have an ion connected with something that's polar. Seems reasonable. I'm going to put a little bracket next to these two. And again, this will make more sense. Hydrogen bonding is a type of dipole intermolecular bonding. Remember, I said, what do you think about dipole? You think polar. So all dipole bonds is you have a polar connected with a polar. That's it. And hydrogen bonds is a special polar connected with a polar. That's it. Well, what else we got? Okay, I said I said dipole, think polar. And anytime you see, and I don't mean to, I always think of induced labor. So when you induce labor, you bring the onset, is everything's ready to go or you need it to go, and the baby comes, you induce labor. Well, if you induce a dipole, you're inducing something polar that's not polar. You're making it do it. I'll show you why that happens. But anytime in this context of this discussion, you see induced dipole, think nonpolar. You got something that's so polar dash nonpolar. Nonpolar. Okay, you must have a polar thing connected with a nonpolar thing. And then the last option we have is induced dipole. So guess what? You're getting two nonpolar things together. Nonpolar. I warned y'all that this whole idea of something polar or not polar, it's a player. And it's a player. Okay. All right, so let's take a look at what this means. And again, the strongest is up here, the weakest is here. Strong, weak. Oh, before we move on, there's a few of them that have asterisks, double asterisks. And notice that they are the ones that are connecting two different things. So this guy right here, you're connecting an ion with something that's polar. Got to be a mixture. This right here, you're connecting something that's polar with something that's nonpolar. Got to be a mixture. Okay. The other ones might be mixtures or they might not be. Okay, so the ion-ion intermolecular force is the strongest of all those intermolecular things. And it's weird to think intermolecular. Well, an ion's not a molecule, it's forming a unit. So if you're like scratching your head on that one, join the club. But it's the word we use to describe that bond that connects the ions. So these could be either. Okay, if you have ion-ion force, ion-ion intermolecular bonds, hydrogen bonding could be a mixture or a pure chunk of matter, ordinary dipole. Induced dipole could be there. Okay. So dipole, I said think polar. So you have two polar things that are going to be stuck together to create an intermolecular bond between them. And they're going to line up with the positives, with the partial positives of one connecting with the partial negatives of another. So here's a little video to kind of show that. Of course, HCl is polar. Molecule A, molecule B kind of doing this sort of thing, or you could have molecule A, molecule B doing this sort of thing where the partial ends. This one's kind of cool because you get two ways that it's they're connected. Those dots are intermolecular bonds. So I said that, or on the list that I printed off for you, hydrogen bonding is it stronger or weaker than dipole? Strong. Hydrogen bonding is stronger. So hydrogen bonding, I'm going to draw it in the corner up here because I'm a visual sort of person. Hydrogen bonding has to have hydrogen. Go figure. And that hydrogen can either be connected to an oxygen, so it'd be like this O-H, and they're right next to each other. If you ever forget about hydrogen bonding, it's these three guys. Okay? So you can have an OH, an NH, or an FH. No. Okay? I usually think hydrogen bonding OH, but it could also be, I'll do it in this order maybe, an N-H or an F-H, which is not very common. The N-H and and those dashes are sigma bonds. The nitrogen sigma bond hydrogen, the oxygen sigma bond hydrogen are more common than the fluorine sigma bond hydrogen. In all of these cases, these guys, guess what? Partially negative, and the hydrogen partially positive. And okay, so you guys probably already know this, but we can have an OH on a molecule just anywhere, and it can hydrogen bond. It's not going to be by itself, because there's no compound called OH. There's no compound called NH. It's going to be a piece of a molecule, okay? So, be looking for those. Those will be, and I have some videos to kind of show you. So this is just simply water, H2O, and that dot, dot, dot is the intermolecular bond between the oxygen from this atom on the left and the hydrogen from the molecule. The oxygen from the molecule on the left and the hydrogen connected to the hydrogen on the molecule on the right. Okay. So when water gets going, you're going to kind of see this whole network thing going on. But that is, do you see where it's dipole? But it's not ordinary dipole. It's hydrogen bonding because the hydrogen is bonded to an oxygen. If you had a hydrogen bonding to a nitrogen, hydrogen bonding to chlorine. Okay. So here's kind of I call it networking, we can have with those intermolecular bonds connecting these 5 water molecules. A high degree of intermolecular bonding, would call that a solid. Looks like there's quite a bit there. Those are all hydrogen bonds. And they're strong. And if they're strong, that means things like we talked about we're going to talk about it, I think, coming up too. We talked about the energy associated with the liquid energy of fusion. That's when you basically melt something. It goes from a solid to a liquid. You break some of those intermolecular bonds. It's going to be pretty high for something that's got hydrogen bonding going on. So hydrogen bonding, what we got? A hydrogen connected to a nitrogen. This is ammonia, NH3. You can see these 2 repeating units. And the dot, 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 again, is connecting opposite the partially negative nitrogen to the partially positive hydrogen. So that's a hydrogen bond. Hydrogen bonding, yep. High degree of intermolecular bonding, I'm thinking maybe solid, HF. And this one emphasizes that the blue there are the chemical bonds. That's the covalent chemical bond where electrons are shared, and then this one, dot, 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 would be connecting these 2 molecules. All right, here's one for you. So here we have wine. This looks like a fun thing to do when you're when it's the end of the evening, you're trying to think of something to do. Take a piece of a paper towel and let it kind of just absorb the wine. Now, it's not going to just absorb the wine. The wine is actually going to whip up the paper towel. And I was looking at this like, how does that work? The way this works is, the thing I'm circling now is the cellulose of the paper towel. I don't know how I want to do this. The cellulose of the paper towel, that's those big molecules. This molecule would be your alcohol, and this molecule would be your water. I was thinking about this in my office, and it's almost like climbing a ladder, okay? And they kind of climb the ladder. They're drawn up it because of their it's a type of exchange process where they're just kind of they're climbing the rungs of the cellulose, which is also polar. Okay? Not just polar, but the cellulose has these OH is hydroxyl. The cellulose has these hydroxyl groups that help facilitate this, climbing the ladder. All right. Hydrogen bonding. Dipole, dipole, which is polar-polar. And now we're up to it. Well, we skipped one. We'll come back to dipole, induced dipole. But I want to go right to induced dipole, which means two nonpolar things. Well, you don't have the partial ends to connect up. So what happens? And this kind of, I think this is cool. Oh, by the way, before we get there, you're going to see me, I like to use the word dispersion forces. And it's the same thing. Dispersion forces means induced dipole, Okay, I don't use London forces as much. Now, we're going to kind of, at the end, kind of wrap up things. It's possible, or how do I say this actually? This slide says that even if something is hydrogen bonding, which is really strong, there's a good chance, or we generally think also, it has this induced dipole also going on. I'll kind of show you how that works. So it's possible within the same amount of matter that's connected together, there's more than one inner force going on. All molecules, including polar molecules, have these dispersion forces. Remember, dispersion means the same thing as induced dipole. So yeah, this will work. Just a minute ago, we looked at H2TE, H2SE, H2S, and H2O. And I don't know if you remember, but actually this heaviest one had the highest boiling point of all three of these. So the way this works actually is, we'll talk about what induced dipole is, but these dispersion forces, induced dipole increases with increasing weight. And actually that's kind of what was kicking in to see this trend. And this trend, of course, was because of hydrogen bonding. All right. So let's take a look at a diatomic element, iodine, and how would an I2 combine with another I2? In all that we've covered, this is only Friday, we've covered Monday, Wednesday, and Friday, and in Chem 1. But you have to think of why would I2 need to induce a dipole? Well, I2 is not polar. Right? I atom, bond between them, they both have the same electronegativity. Okay, so you have to induce a dipole. And it happens in even polar things. So this is I2. The purple haze here is I2 gas. I2 is one of those things that sublimes. It goes directly from a solid to a gas. Okay. This is Br2 in its liquid state and Br2 haze. So the fact that it can actually exist as either a solid or a liquid is proof that solids have a high degree of intermolecular bonds, liquids have a lesser degree of intermolecular bonds. But of course, the fact you can get it to do that means that you must have an induced dipole. You must have had and somehow gotten them to connect. And it's induced dipole. Okay. So how well can you induce a dipole onto something that's nonpolar? That actually is summed up in the term polarizability. Okay, so polarizability, can you shift that electron cloud like we saw with those two I2 molecules? How hard or easy is that to do? In general, the more electrons you have, with tellurium having 52 protons, 52 electrons, the more likely you are to kind of move things around, the more polarizable it is. And if it has a higher degree of polarizability, then you can go ahead and get a dipole induced where there isn't. Larger atoms are also better as far as getting a separation, partially to inducing they're more polarizable, getting separation of the electron cloud. And in general, as you increase the molar mass increases up there too, more polarizable. So I have some terminology, and I usually have to kind of make sure I remind myself of how this works. Van der Waals forces, which I don't use that term very much, but just in case you run into it, OpenStax uses Van der Waals forces to talk about anything without ions. And so that leaves your ordinary dipole-dipole, your dipole-induced dipole, and induced dipole-induced dipole. But some textbooks use that same term to talk about only the dispersion forces. Remember, I like dispersion forces. It means the same thing as induced dipole, induced dipole. Put it on mine, so you should put it on yours. I'm telling you, when I do homework, when I did homework, I print this off for me. I print it off for you. So let's take a look. Let's take a look at some, how do we gauge intermolecular forces? So these are just two things stuck together. Of course, F2 must be nonpolar, right? HCl, polar, polar, polar. And you can kind of see how the masses are. The net dipole moment, which would be the same thing as the dipole moment since there's only one bond. Notice that HCl has the strongest net dipole moment. If we were to go ahead and say, and the next slide kind of does some evaluation too, if we were to, for each of these four, kind of look at how much do you have the dipole-dipole intermolecular bond versus how much do you have that induced dipole-induced dipole. Notice the F2, it's not polar, so it's all the dispersion or induced dipole and induced dipole. But even with the HCl, notice that that has the highest dipole moment. It has the strongest amount of its intermolecular bonds, then has that dipole-dipole intermolecular bond. But a fair degree of it is still those induced dipole dispersions. Okay. Notice the HI that has the lowest, weakest dipole moment, net dipole moment, actually has when it connects with other HI molecules, with regard to intermolecular bonds, only 0.5% of it is the dipole-dipole. And the rest is induced dipole. And then this last one over here is actually a better indication than even the boiling point. This is the latent heat of vaporization. So let's see if we can see. It looks like it's trending from HI has the strongest, the highest heat of vaporization. Now, one of the reasons you might say, well, HCl has a stronger dipole moment, but HI is more polarizable. Why would HI be more polarizable than HCl? HI more polarizable. More electrons, exactly. More polarizable. So then what kicks in is it's more polarizable. So it's not the dipole that makes it so strong and hard to vaporize. It's the induced dipole, those dispersion forces. What else we got? One more column? Boiling point temperatures. And is this right? No, I guess this is pretty. Actually, there's a law we're going to talk about later that notice for these same substances, for the same substance, if you look at the heat of vaporization, it correlates well with the temperature at which it transitions from a liquid to a gas. So, for instance, the HI had the highest heat of vaporization, and it also has the highest boiling point temperature. F2 had the lowest heat of vaporization. It has the lowest boiling point temperature. Last slide. So this actually, I'm going to kind of reveal it from left to right. There are three possible forces here, and the blue line is the total force. So for argon, you're like, okay, how do you get an argon atom, right, to stick to another argon atom? Well, argon's a gas in normal temperatures and pressures of Earth. So argon would be nonpolar. So you're only going to be able to get induced dipole, those dispersion forces to hold it together. Carbon monoxide, seems like it would be polar. must not be very polar, because it's showing that when carbon monoxide sticks to another carbon monoxide molecule, what kicks in is just the induced dipole. HI, you got a degree of polarity. We talked about the HI, HBr, HCl a minute ago, where the I, Br, and Cl are all those halogens connected to a fluorine. Again, the blue is the total, the yellow is the dispersion or induced dipole. Now, here we have this blue kind of picking up right here. Blue is the dipole. Remember, HCl had the strongest electronegativity difference, the greatest dipole, so it has the most, the strongest in that sense. But HI, you guys told me, since iodine is larger, it actually overall has higher forces because that induced dipole kicks in. Now we have what's so special about these last two? What do they have in common? They're hydrogen bonding, yep. Ammonia, NH3, and water, H2O. Whoa, so you can see where their total intermolecular forces are higher. Which one is it, this light blue? Okay, wow, this light blue. This doesn't happen to kick it out, the ordinary dipole versus hydrogen bonding, but hydrogen bonding is a type of dipole. So here's your hydrogen bonding, this tall one here, this tall one here. Dipole, induced dipole, we'll talk more about that on Monday, but it's also happening in those liquids.
So, find out something that's hydrogen bonding, I'm supposed to know.
All you have to do is, and you'll pick this up as we do some more examples, but you'll look at the molecule, and if anywhere on the molecule you have an oxygen with a hydrogen, kind of a little tag, or if anywhere you have a nitrogen with a hydrogen, or anywhere you have a fluorine with a hydrogen. Yep. And you can have multiple sites, and it makes it even stronger. So, yep. So, but you might have to draw the Lewis, because Lewis structure are taken drop there. You might have to draw the Lewis structure to kind of understand how things are connected, and if that's a possibility. So these will be due on. You have to watch for the eclipse. I'm hoping there are all sorts of eclipse stories on Monday. But oh, that's right. But we may or may not have this because they might ask some great questions and have a good time at the Martin Luther King celebration. All right. Have a good weekend, guys.